In this lecture, we will be learning about the arc length parameter of space curves. Recall, the arc length of a smooth curve given by r of t equals f of t, g of t, h of t, a vector-valued function, for t between a and b, that is traced exactly once as t increases from a to b, is given here. L is the integral from a to b of the magnitude of r prime of t, or the magnitude of the velocity vector. We're now going to expand on this a bit, and we do this by fixing an initial time. So an initial value for the parameter t naught. And so at time t naught, we will have our particle moving in space, tracing out this smooth curve at this point here. And then as we run the clock, the particle will move and trace out our smooth space curve. But what we want is to define a new function, s of t, which will give us the arc length traveled by this particle from time t naught to time t. So at time t, s of t is the length traveled by this particle from time t naught to time t. And this is how we define it here. So the arc length parameter with base point r of t naught of a smooth curve, r of t, for t greater than t naught is, here mathematically, we see it's exactly what we just described. This gives us the integral for the arc length, but we start at time t naught and we end at time t. Note we had to change variables. We're using t now in the upper limit of integration, so we need a dummy variable. And we just, for integration, and we just choose tau. Usually we use s or t, but you can see we're using them both here. And of course, when you do this integral, you're integrating d tau, and so tau does not appear in the result. So it's just a variable for integration. And again, t naught is the initial parameter value. To think in terms of applications, one setting where you would use this would be if you were designing a drone. So if you're designing a drone, you would want to put an odometer on that drone. And so you could program a routine where at time 0, your drone starts at the origin, and then as you run the clock and the drone moves in space, at any time t, s of t tells you how far the drone has traveled. Which is going to be helpful for things like fuel consumption and just keeping a record of the path of your drone and how long it is. We now look at the arc length parameter, so we have the definition given here, and we note that if we take the derivative, things work out quite nicely. So if we take the derivative of s of t, we get s prime of t, and on the right, the derivative with respect to t, because the variable t with respect to which we are differentiating is in the upper limit of the integral, the derivative of this term is the integrand, the magnitude of v, with that t plugged in. So we see that s prime of t is the magnitude of the velocity vector. So you can think of this, if we think about what derivatives mean, the instantaneous rate of change of the arc length at time t is the magnitude of the velocity vector, or the speed, at time t. So the faster you're going, the higher your speed, the higher the instantaneous rate of change of your arc length. We're going to see a very important use of this idea of arc length parameter in the next lecture, where we start to get into something called the TNB frame. And that's going to become important because we are going to reparameterize our space curve in terms of arc length. So let's talk about what that means mathematically, and then we'll talk about it, what it means intuitively. When you do this arc length parameter, you have s of t. So s is, in the end, just some function of t. And the question becomes, is it invertible? Can you solve for t in terms of s? If you can, think about your r of t. R of t is our position vector for our particle moving in space whose path traces out our smooth curve c. Well, t is the independent variable. But if t can be written down as a function of s, we can substitute that in here. And now r would be a function of s. So r would be reparametrized in terms of arc length. And this is really convenient because if you think about the way that we define the parameterization of a space curve, it's focused on a particle moving along it. When we parameterize in terms of arc length, we're parameterizing based on the path itself. So if you think about parameterizing, say, a path of a roller coaster, the way we're doing it in time is parameterizing it based on the movement of the car on the roller coaster. But parameterizing it in terms of arc length is just parameterizing it based on the track itself. And so this is something that will be really handy going forward in the next lecture. But let's take a look at an example and see what it means to reparameterize a curve in terms of arc length. So let's look at our classical example of our helix. R of t is cosine of t, sine of t, t. And we'll start with t naught equals 0. And we want to reparameterize this curve with respect to arc length. So first, we need our velocity vector, which we know is minus sine of t, cosine of t, 1. And the magnitude of this velocity vector is root 2, as we derived in the previous lecture. Thus, our arc length parameter, s of t, by definition, is the integral from t naught to t of the magnitude of v of tau d tau. T naught in this case is 0. So integral from 0 to t of root 2 d tau, which we see is root 2 tau evaluated between 0 and t, or root 2 times t. And so what this means graphically is we start out here at time 0, and then at time t, this s of t will be the arc length of the curve that has been traced out from time 0 to time t. And you see it's a function of t. So as t increases and the particle moves more, this is increasing. We see that its arc length is actually increasing. And note we were asked to reparameterize this curve in terms of arc length. So this says that our arc length, right, we have S is equal to root 2 times t, which means t is S over root 2, or root 2S over 2. Which means we can now reparameterize by substituting t in here. That gives us r of t equals cosine of root 2s over 2 sine of root 2s over 2 and root 2s over 2. And this now is a reparameterization of our space curve, of our position vector, in terms of arc length. And so what we've really done here is, instead of r of t, we now have r of s. And again, this now tells you the position of a particle as a function of how far the particle has traveled. And it's just a different way of parameterizing it. And this is going to turn out to be really handy when we look at the next lecture, because we're going to start to care about questions like the path that this particle is on. How bendy is it? Is it twisting? And this arc length parameter and this reparameterization concept is essential for that.